are we ready to launch into semi-ring dictionaries?
Sure.
So I was mostly intrigued by this paper when Sergey mentioned it, and I read the abstract, and I realized I knew almost all of the words in the abstract, but I couldn't picture what they were talking about. How did those words go together? And so anyway, now my question has been answered, and I have a rough idea at least of what they were talking about.
I have
When
a
I
rough
first looked
idea
at
of what they
this,
were
yeah.
talking about, but some of the details, like their examples, just didn't work for me. But
Right, I noticed that you and Hugh have been posting on the Slack quite a number of questions
yeah,
about exactly how it works.
not that much, but yeah, a little bit.
My main question was, well, I thought they're going to propose some kind of do notation for all this, right? So because they're kind of they're generalizing the map, flat map, and so on functions to a database query, so that you can have both the usual map reduce type programming and the database type programming in one package. That's how I understood it. But my time to look at it was very limited, so I didn't see any do notation in their paper. Like, how are you supposed to use this stuff? Are you supposed to just like call functions, like methods? On these semi-ring dictionaries, you just say this is a semi-ring dictionary. Now I can add it to another semi-ring dictionary or whatever, right?
I think that's
Right,
the
well,
idea.
yeah, it's an external DSL rather than an internal DSL, so they don't talk about the representation of the data in whatever language you are calling the database from.
Didn't they mention a Scala library?
Yeah, they said something, but they didn't give us any
No,
syntax for calling it from Scala. I mean,
right.
I guess
I
the
think they
library
said it was they said it was built in Scala, right? Or most
okay.
Scala.
Now, what does it mean it was built? They built an interpreter for this language in Scala?
Yes, it's a specification, and I believe also an implementation, because they have notes at the end on performance.
But they did not publish it, right? Implementation is not open source.
I don't know.
I couldn't locate it.
Yeah, I don't know.
Okay, it probably isn't then. Yeah, and I come to think of it, I didn't see them mention either map or reduce. Do they have any map or reduce examples?
I didn't see a
I'm
way
not
to
sure.
apply arbitrary functions.
I guess
I
they
mean, they have multiplication with a scalar, right? So if you have a dictionary and you multiply it by a scalar, you'll just
you get a map. Yeah.
multiply all the elements by that. So that's a specific form of map, I guess.
And
But
they
only,
do have grouping or like aggregation, like I'm familiar with from SQL. Right? So you can group by something and then add up the groups and stuff like that.
Right. So one of the big limitations is that their data types don't have any recursion as far as I can tell. So you can't represent an arbitrary data structure. It's sort of you have to know how deep your data structure is going to be ahead of time. You don't do arbitrary recursions over data.
right. I mean, they sort of have a fixed type system with, where are they? Like the types are just the dictionaries and records and scalars and whatever U is. So that's sort of their universe there.
Right, I think
Don't really give you a way of defining, like you say, recursive things.
yeah, I think U is the scalars that are not semi-rings.
Yeah.
Maybe someone should share their screen so we can all look at the same page.
Right,
Did I do that?
be literally on the same page, yes.
Yes. I'm volunteering, Pete. Thank you.
Move some of the stuff out of the way. Some of the stuff over here. Oh shoot, that didn't work. Okay, so that's not the beginning. So I guess what I was just referring to was this chart.
Right,
So we have the types T, which include the dictionaries and records, and then these are the semi-ring types in real bool, and then they refer to table 1 for more of them. And then U are just types that aren't semi-rings. So we have string and dense int, which I think is something when you use it as a key, you have basically the adjacent numbers as your keys. So it's basically more like an array than a dictionary. But I guess that's in the future. And then there's two kinds, type and SMS. But I wasn't sure what SMS, what SM stood for, because in some places they say that it's the kind of semi-modules, in other places they say it's the kind of semi-rings. So I'm not sure. And
right.
and if it is semi-modules, I mean it seems like this is the key thing, right? That's in the title is semi-ring dictionary. So you'd think that dictionary would be sort of their key thing. But here everything is like semi-module kinds.
Dictionary is a vector space. Dictionary is a vector space, and even nested dictionary is a vector space. I mean, again, if you think about field, not semi-ring, if it's over a field, then both dictionaries and nested dictionaries form vector spaces. So suppose that in their generality it becomes some sort of modulus.
Okay.
Right. I don't think it's a module in the sense that programmers usually understand the term module.
No. It's algebraic algebra. It's what algebraists understand as modulus, the vector spaces, which are not all of the fields, things like that.
I see.
I mean, it's algebraically right. It's a set with plus and scalar times. Is that right?
The semi-ring? Yeah.
The semi-module.
Oh.
The semi-ring has plus and times 0 and 1, and but I think the modules just have plus of 2 modules and then times of the scalar times the module.
Ah.
The semi-modules are all like parameterized by a semi-ring.
Yeah,
I think
that's exactly right. So semi-module you say semi-module, you always have to have in mind a base semi-ring, but it's like it's a module over S. So when it
Yeah.
says SM of S is a type, you know, S has to be fixed. And then you can talk about all the semi-modules over that one, and that forms a kind, I guess.
Hmm.
Although I'm a little unclear on that.
Right. So I guess dictionaries end up being semi-modules and records also. So maybe that is the key thing.
Right.
Yeah, I think if your value type is a semi-ring, then a dictionary then the set of dictionaries or the set of records will be a semi-module. It'll have a semi-module structure over that semi-ring, I believe.
Ah. Right.
Yeah.
Right. So I guess, yeah, you can build these things up in such a way that they are always following the semi-module laws, which are the things they present in section 2.1. I guess it's the fact that they follow the laws that enables all the optimizations that they talk about later in the paper.
Yeah, I think you're right. And I mean, I don't know how if those laws rule out useful things, but they sure seem to have a lot of examples of useful things that aren't ruled out. So I guess that's good.
Right. I think, yeah, you can't put arbitrary data into this format, but if you happen to have data that do follow these laws, then you can do all these things they talk about in the paper with them, which, yeah, there do seem to be a fair number of examples that for which this kind of database is useful.
Yeah. Maybe should we sort of go through? Oops, I just darkened my screen. I don't know if you saw that, but so you know, this is the language. Up here, we just went through the types and expressions, like this aggregation thing that we could talk about later. These are the things that form dictionaries. This is an empty dictionary. This is application. These are records, record selection, not E for Booleans, regular let, and a variable, if then else, plus times. I wasn't sure what promote was.
It's just a cast from one type to another.
Okay.
So, yeah, generally from a numeric type to another numeric type, I guess.
I see. Okay, and then I guess this is saying all the numeric constants, real constant, false, true, and C. What's C?
I guess a constant that isn't real or numeric. I don't know.
Yeah. Yeah. Other constants. Okay. And then, right, we have semi-rings, which have the plus times and plus and times, and you know, has all these laws, so it's distributive, like all over, you know, I guess all the different ways. And then 0 is the unit, 1 is the unit for times, and there's some associativity in here too. Times is associative. I think, yeah, plus is commutative.
And associative.
Yeah.
Yeah, so particularly interesting use case here is that they can be rings of matrices instead of usual rings of numbers. I think that gives a lot of tempting complications. But
Mm.
Yeah, I was just wondering why they are calling it a semi-ring, and I looked up. It's the only operation that makes it so that it's not a ring is that there's no inverse for the addition. A ring has a minus a. For each a, there's a minus a that adds to 0, but they don't
I
have that
see.
here. So that's
okay,
the only.
so
Mhm.
okay, so this means that this covers interval numbers too, because conventional interval numbers, unless you do some interesting manipulations with them, they are semi-ring in this sense. You don't have negation for addition on things which are not precise, because addition cannot shrink and 0 is precise.
Right. Yeah, I guess it doesn't make sense to like negate a dictionary or whatever.
Could negate the values of it. You couldn't negate the keys if the keys are strings, something like that.
Mm.
But I think they might want is there like a positive in it or like a non-negative integer type? Because I would
Like
expect
natural
that would be a-
numbers,
yeah, natural numbers. I would expect that to be a semi-ring, but not a ring, precisely because we have no additive inverse. You know, we don't have the negative.
Right, they
Right.
list on page 5, they list the various data types that they can apply it to, and so
Natural,
both
yeah.
natural numbers and integers are possible.
Mhm.
Yep.
right?
And the min and max examples are similar.
Mhm.
You can go up
Right.
but not down.
And Boolean operation under or and. That's interesting. Okay.
That's true. That also does not have an inverse, I believe.
Right.
Right, so at the end, when they're talking about possible language extensions, they do mention that they could actually implement this for rings instead of just semi-rings.
Hmm.
A ring is a semi-ring, right?
Yes, semi-ring with an inverse for addition.
Right, right. Then you get, I guess, a little more power.
Or I guess specifically a non-commutative ring. Just to be technical. Usually when people say rings, they want the multiplication to be commutative, but ours is not necessarily.
Hmm. Right.
But that is pretty cool. Like, so they've identified a bunch of laws, you know, which hold in this pretty broad range of examples, and which also is powerful enough to, I guess, to give them all these optimizations. Because I assume that the optimizations, like Adrian was saying, they're all justified by the semi-ring and semi-module laws.
Right, I think that is the idea.
And the natural numbers they actually do use. They haven't. I honestly didn't understand the genetics example. I think the exposition is not that great, but I did understand that they were using bags. They were like or multi-sets, right? They were having sets with multiplicity, and that maps very cleanly to the, you know, I guess dictionaries which take values in the natural numbers.
Right. Sort of your standard dictionary just maps keys to true or false. And well, I guess I'm talking about sets. Never mind.
Yeah.
Okay. So scalars, that's kind of what we were just talking about. Boolean, I don't know. Promotion, that's kind of what Adrian was just saying. It's a way to coerce from one type to another. Dictionaries have this kind of type. They have a key type and a value type, and then a particular dictionary is written in that form. Key, arrow, value for as many keys as you have. There's an empty one. And then one of the problems, okay, so then they're saying if V is a semi-ring, then the dictionary forms a semi-ring structure, right? But the thing that confused me is that, like, if you have two of these dictionaries and multiply them together, right, you end up with these sort of nested dictionaries. You end up with A going to a dictionary, and then B is going to a dictionary. So it's, I thought in order for it to be a semi-ring, the multiplication should be from element cross element to element, right? I mean, if your type is S, your operations are S cross S to S for plus and times, right? But this is like taking like a dictionary that's KV and a dictionary that's KV and going to a dictionary that's K of dictionary of KV, which doesn't, to me, doesn't match the type.
Yeah.
Is it
That's a
some
good
kind
point.
of tensor? Is it some kind of tensor product or something?
Some kind of way.
Some kind of tensor product? Is it that's what it is? When they
Well,
multiply.
yeah, they do have this tensor product, and maybe that is where it's going. I thought the tensor product was more like had pairs, but maybe that's only for certain things. I don't know.
Oh, I'm actually looking up above in the middle of the page, where it says
Okay.
if the value elements with type V form a semi-ring structure, so if the values are from a semi-ring, then the dictionary forms a semi-ring structure where the addition is pointwise. Yeah. Yep, you're right. We should be able to multiply them and then get back the original type. So now I'm confused. I understand the module part. Multiplying by scalars is no problem. But I don't see how we're getting back to the original type when we multiply two dictionaries. Huh.
Yeah, because we end up with,
Peter, are you
yeah.
saying that you think the correct operation is that after you do this multiplication, you should still have a type of KB?
Yeah, that's what I would think that.
But I would argue it's actually incorrect operation if you think about it, because their dictionary require you to have a unique key. And then that means you will have to go through a flatten and then remove the duplicate key. How would that work? If but if
I'm
you
not
look at
sure
their
what you're
definition,
saying.
I'm saying that if you, instead of a nested structure like they do for multiplication, you want to go back to a KV type, highly likely you will have to do a flatten of the inner dictionary, the nested dictionaries, and then all of the duplicate keys, somehow you have to reconcile them, right?
Right, you could do a pointwise product where you just multiply the entries from, or two entries with the same key. But
Yeah, I mean, you could come up with a dictionary where the keys are pairs, K, cross K pairs, and that would sort of be the same thing. It's just a curried version. This is curried of that, I guess.
But that also changes the type though, right?
But that
Yeah.
still changes the type. So yeah, it kind of seems like what Wayne was saying is kind of what I was expecting to see, that there was some sort of flatten going on here that would bring it back down, but I don't really see that.
Yeah,
At least not from this example.
but at least I think their examples still preserve the semi-ring by keeping it a netted structure. And as you say, if you try to change the key type to be a tuple, I think that probably also works.
Right,
Huh.
they talk about the difference between the curried, non-curried representations of dictionaries later. They are equivalent.
But doesn't, you were saying that it would work, that we can, I mean, if if the result type is like you know,
K, comma, K, or something like
K, yeah, like K arrow V, right? But
yeah.
I would think a semi-ring, all the operations should be on these K arrow V things. You're adding them, you're multiplying them, but your range is the same thing, isn't it? It's always, these operations are sort of closed over
Yeah,
whatever
it should be,
the
if it's going
element
to be
type
a
is.
semi-ring, it should be closed under multiplication. Absolutely. I would think. Right.
Right. But yeah, maybe it's enough that the keys are the same. I don't know.
Right, maybe if you ignore the types and the fact that the laws are followed, maybe that is sufficient.
Hmm.
I kind of agree what Adrian is saying, is because at least you still keep the semi-ring structure, or I should call it semi-module. And this you can build up based on that, because your laws are still the same. And then looks like your type has changed after the multiplication.
Hmm. Yeah. Okay.
That's it's type
So
dictionary.
maybe this is a, go ahead. No.
It's type dictionary. Is that what you're saying?
Right,
Yeah.
well, dictionary type is
For the value?
yeah, a dictionary type is there isn't just a single dictionary type, but there are different dictionary types based on the keys and the value types.
Right.
So if you've got a a string to nat, that's different from string to nat.
I'm just trying to get the concept of rather than type T to T, it's going from type T to type dictionary T, I guess. Is that's kind of what I'm seeing. That's what that's I think what you guys are discussing, right? It's like it doesn't seem to be closed under.
Yeah. It seems like if we multiply the dictionary,
Yeah, if you have
of
two different
KV,
key types, suppose it's
it
a
should
K1.
end up being K to V, you would think.
You would think,
Well, maybe I should write multiplication out here.
right? Potentially
But
there are
anyway.
two different key types, so there could be a K1 to V times a K2 to V. And what you appear to wind up with is a K1 to K2 to V.
Right. But my understanding of it, yeah, and I guess what we're saying is our understanding of a semi-ring is that you have your plus and your times, and they're both whatever the type is. More like that. Or
So what are the,
maybe
is there a
maybe this is
dictionary
done.
type? Sorry.
Not a
Is-
single dictionary type.
Right. But is there, for example, a string to int dictionary type?
Yeah,
Yes.
I'm
yeah.
looking at the
This
type system
this
and I,
is the syntax, right?
yes.
This is the syntax. So K could be string and B could be int.
Oh, it is a type. Okay, I can actually see that in the, I'm looking at the list of kinds, types, and stuff in page 4. I just wanted to confirm.
The wait, where's
Sorry,
page
farther,
4?
It's
farther up.
above, yeah. Talking about the syntax, the expression, and types.
Yeah,
Go
this
up.
page. Okay. So actually at the very
Yeah.
upper right, it looks like it's confusing because string to int is a type, but it's also often a semi-module kind, right? Just at the upper right of figure 2,
Hmm.
T1 arrow T2 is a type, I believe, always.
Yeah.
But T1 arrow T2 just above it is also a semi-module
On S. Right. I mean, the
kind.
difference is that T2 is a semi-module on S here, but here T2 is just a type.
Right, okay.
So if it's just a type, then the dictionary is just a type. But if
So it
it's a
does seem like
semi-module, then this is a semi-module.
it does seem like they're saying that string to int is a dictionary type.
Yes, but later down below, if you look at the rule in the next to last box in this figure, same figure. They have the
Next
type,
to last box.
right, that would be the rule with the result E1 times E2 is a tensor product of T1 and T2. So it isn't a T1 or a T2, it is a T1 tensor product T2.
Wait, so tell me, where are you, what are you
So if
looking
you're
at here?
looking in this figure, figure 2, you go up to the third line from the bottom.
Like here?
That's it.
Or,
So that's the one that tells you that the
oh,
product type is not the type of the argument.
But then right below that, though, we have a definition of the
oh,
tensor product, and it's just a nesting, right? So
is that what this says? I didn't quite
that's how
get it.
I'm interpreting it. That if you have you know, T1 arrow T2 tensor product with a T0, then you're just pushing that T0 into the T2 part and tensor producting it with the value type.
Mhm.
So that's the
And
nesting.
and ultimately, the rule just to the left of that says that when you tensor, ultimately we're going to get down to S, right? Because that's the only way we have of constructing semi-modules over S is by using the semi-ring S. And ultimately,
Right.
when you tensor with S, it has no effect.
Yeah. Yeah, I think
It has no
what's
effect on the type, but the values are
Yes,
multiple,
yes, right.
are scalar multiplied, right?
Yes,
right.
exactly.
Yeah.
Okay. So how does that resolve the question that I was bringing up?
I don't think so. They
Right,
do.
well,
So I see that Adrian, so Adrian's pointing out like the third from the bottom there is a definition of it's a definition of star, right? This star operation where you have two things which are both semi-modules over, you have two values which are both, no, sorry, two semi-module types over S.
Right, we have these
Have
two.
values
They're
of those
both
types.
semi.
Yeah, then you can take a star of them. Yes, but they do say, I think this is not, they do say down below under tensor product, they admit that they are overloading the symbol star, right?
Right. So
Mhm.
is this the tensor product star or the?
I think it's the tensor product star.
But it's actually both, because if you look down to the next line, it says S tensor product T1 is T1. So if you have two S's, then it will wind up being just S.
Yeah,
So that's where the scalar rule falls out of the tensor rule.
yeah.
Mhm.
Okay.
Yeah, I
So I
still haven't
guess,
resolved
Yeah.
the.
So just okay. Go ahead.
Oh, I
Right.
still haven't resolved Pete's question, because it really seems like they want the dictionary type to be a semi-ring.
right, I think it's a semi-module rather than a semi-ring, and the distinction seems to be that the type winds up being this nested tensor type rather than the original type.
That I could believe, because in a module you don't expect to be able to multiply two things, right? You only multiply them by scalars, and you can add them.
Right, well, it appears you can actually multiply two modules, or you can multiply two dictionaries. And so that's what they're providing the rules for.
Yeah. Okay. Maybe it's just
So
one.
would this be the rule for multiplying dictionaries?
Right,
Sure.
that's the typing rule for multiplying dictionaries.
But not all dictionaries are semi-modules though, right? I think
Um,
going back
No,
to figure
you're right. They're not all.
going back to figure one, this is a little bit confusing. There's the type of dictionary, which is TROT, but then how do you generate a semi-module over S?
I think
It's
it's a
not clear.
semi-module over S if the value type is a semi-ring or semi-module.
Okay,
So
that's what's
basically,
confusing to me because they're using the S two lines above as scalar type, int, real, or Boolean. And then there's this confer table one. So where is table one? Okay.
It has
So
these
so these
things.
other types are also scalars. But then K, kind can be either a type or a scale semi-module over S. So that's why I'm interpreting S to be scalar here. But then I'm
Right.
not sure how to distinguish what is a semi-module as opposed to, so everything is a type, but some types are semi-module over S. Is that right? And so not every dictionary is a semi-module. That's my interpretation.
right.
Right.
I think,
If the dictionary result type is like string is not
right.
Correct. Right.
the semi-ring type. So
Right.
that
But
won't
then
be.
but then if the target type or codomain is a semi-module, then the dictionary over it is also a semi-module, right?
That's what they seem to be saying.
Yeah.
I think
Okay.
so.
Yeah,
Okay.
I think they say exactly that in the figure 2, the big box of derivations.
Yeah. Right.
That's the upper right thing. So if your key, so the upper right, yeah, thank you. The key comes from any type T1, and your values are in any semi-module over S type, then the dictionary is also in
Okay,
the module over S type.
yeah.
Maybe it's a
And
kind.
and then the
But anyway, I think that's
and
what
then
you were saying.
Yeah.
right, and then the base condition is on the left there, right? S colon colon semi-module over S. So any scalar type is of that. Okay.
Well, any
Is a semi-module
scalar,
because you could just throw away the operations.
yes, any scalar type is a semi-module over itself specifically,
Right.
right? Yeah.
Which just means, right. So in that case, the multiplication ends up being S cross S to S.
Right.
Yes.
Yeah.
Right. Which is what we would expect. But okay.
But then starting with that trivial semi-module, you can build up more interesting things like the matrices that we were talking about earlier, and dictionaries and so on.
Yeah, so that is restrictive. I that a semi-module is always defined over a specific scalar type. And
Yeah.
then you have to preserve that in your constructions going up. Okay.
Yep. So it's going to be like
Right.
maybe sets or relations or bags or
Your semi-modules are those kinds of things. Yeah.
yeah, sorry. So if you take S to be Boolean, right, then
Mhm.
semi-modules over S are basically the sets. Is that right? I think that's right.
Well, at least dictionaries
Into Boolean.
into Boolean or sets.
Yeah.
And if it's into int, then they're bags.
Oh, that's true. That's true. You
Right.
also have records, which are records are not don't feel like sets. Okay.
Hmm.
So I guess the sets are the sets are a subset, a subclass of the semi-modules over Boolean.
Yeah. I mean, yeah. Sets are of that type where T2 is Boolean. So you're just constraining this rule a little bit. But okay. Anyway, I still don't know the answer to my question. But so
Somebody,
tensor product.
oh, sure.
Go ahead.
In that big hairy box under type system, can somebody interpret for me the symbols? So we have gamma turnstile E is a
So gamma is usually an environment, which is, variable colon type, a bunch of those. And then E is an expression and T is a type. And you're sort of saying in this environment, this expression has that type.
I see. So in any particular context, if you have some values of a type, this gives you rules for generating probably more values of that type or some other type.
Right.
Right.
Is that right?
So this is sort of the key rule for getting things out of the environment. So if in environment, you want to know that K has type T, well, you say is, X colon T in the environment. And if it is, then you can say that X has type T. That makes sense?
Somewhat, yeah.
Yeah,
a gap,
look at the first line of the type system. And then the first inference is if constant is of type T, then under any environment gamma, that constant is still of type T because the constant does not have any free variables, right? And then
Right.
the next one is if some variable X is of type T, that type declaration is part of gamma. So gamma is a set of these type declarations over variables. If X type
Right.
T is an element of gamma, then obviously gamma with gamma, you can say that X is of type T. And then the induction is on the other ones where, E1 can contain some free variables which are captured by gamma. And then, you can do the let by taking X of type T1 and then any expression E2. So,
Right. So let you have an E that's a T1 in this environment, but then you extend the environment with X being T1 when you prove that E is in T2.
mhm.
And that allows you to get that the whole thing is a T2.
Cool.
Right.
Thank you. I just
Okay. Yeah.
not super familiar
That-
with the location.
That is it called turnstile?
Yes.
Turnstile. Yeah.
Is it similar to the colon symbol in a sense?
Not quite. Not quite. Colon is a relationship between the expressions of a language and the type, right? So,
Or in math though, in math within like, I guess such as.
It's kind of like implication. You're saying if all of these things are true, then this thing is true.
Or within that environment gamma, you have, let's say, expression one of type T1.
mhm.
Is that
Well,
turnstile?
gamma always has variables. So it's, X has type T1.
Gamma is the
You know what
environment.
I'm
though.
saying?
Well,
Right.
you should imagine that you're the compiler. So you're looking at the program code, and you have you're writing down what variables the programmer has defined and what types they have. So that is gamma. That is a list of those variables. So the programmer so
And
far
there are
has
things
defined
of this
X,
form.
X and Y and so on, and they have types that we already know. So that is the environment. Now we're looking at a new expression. So, which is to the right of the turnstile. So gamma is to the left. And we're trying to say, well, what is the type of that expression? For example, E2, well, if you're looking at one of those, right? Given gamma, E1 has type bool. So what does it mean? It means that E1 is some expression. For example, if X greater than 0, then true, else false, or something like that. Right, so then that's an expression of type bool, because X and Y are expressions of type integer, or something like that. And that is in the environment. And so
And so
these
that's
are,
what turnstile is saying that, right? It's saying these types of expressions exist within this gamma environment.
the turnstile says, if we have them in the gamma in the environment, then we can prove that the expression E1 has type bool. So, or we can recognize that it must have type bool. So we are, in the rule of the compiler, we're trying to type check the code. So we're trying to figure out what types different expressions will have. And so at any point, we have already found that some expressions have some types. And that's our gamma. So now we're looking at a new expression that's to the right of the turnstile. And that's how I read that. So these judgments say, if we already found that gamma has certain things, and from that follows that E1 has bool, and E2 is T, and E3 is T, then we can prove that the expression if E1 then E2 else E3 has type T. So this is one step of type checking. So
Okay.
this is how it works. So then once we have proved that, we can look at some other judgment and go on with other type checking with of further code. So each of these rules are supposed to give you one step, and then if you have a big program, you have to split it into steps and then go through the rules as necessary. And eventually you should type check the entire code. Initially you have no variables. So gamma is initially empty, usually. And then you go on and you get new variables and more variables. And then at the end of your type checking the entire program, you have found that all the variables that you have seen are already in the gamma. And the entire program is to the right of the turnstile. And it has a type that you have found. And then you read the programmer's code, and that has a type annotation. Then you check if the type annotation is correct, and you say, yeah, yes, everything is fine, or no, this is a type error. So this is how I would read that.
So it's
one way to
turnstile
interpret the turnstile is that it's like for all of for any binding of the x's of the appropriate type, that this expression will have that type. It's kind of like a for all.
Okay, I'll
Go ahead,
thank you.
whoever. No.
Yeah, that helped. I need to think about it a little more though. Thank you.
Yeah, maybe one concrete example might help. Pete, can you write on the line type system x:(t) is an element of gamma, right? That just says that gamma.
This one here, is that what you're talking about?
Yes. Write gamma is equal to the set x:(t). And then the line below it then, set containing x comma t, turnstile x:(t). Okay, put the is that gamma on the left there? Yeah, that's it.
Yeah, it's supposed to be.
Okay. So then you should think of gamma as a set of assertions that says x is of type t, y is of type some other type, and so on. Then, basically you're saying from a collection that contains assertion of x of type t, I can prove that x of type t, trivially, right? Because we've already said x is of type t. And then things get a little bit more complicated on the second one, where you've got the t turnstile E1:T1, and then the next one, gamma, comma, x:(T1. This comma is just saying add x:(T1, union that singleton with the set that's already in gamma. Okay.
Right.
So now we have on the left side of the turnstile a set that is all of gamma plus x:(T1. And then that can, from that, if we can show that is E2 has T2, and that's what the horizontal line means, assume the two above, that gamma turnstile E1 and gamma comma something turnstile E2, then we can conclude that gamma, from the original gamma, we can then show that the expression let x equal to E1 in E2 is of type T2. So this is the kind of notation that's used in programming language types using, I guess this is called operational semantics or something like that.
Yeah,
Well, this is not
it's very
semantics. This
dense.
is type checking.
It's very
Right.
dense. There's a lot packed in there. So
Yes,
I know.
yes.
It's like they could
a
have used a
mathematical
little bit
notation.
more white space.
Yes.
okay,
Right.
thank you.
Right. Okay.
Question from my side. Must we know what gamma is, or might it be enough to say it follows from gamma?
We're saying
think
that this is true
follows
for all
from.
gamma. We don't know what gamma is, but this rule will be true for any gamma.
Right. But the things above the horizontal line are the assumptions. Right?
Right. The premises, yeah.
So if we have such a gamma that can prove E1 is of type BT1, and the other one, yeah, and gamma plus X is of type B1 as the environment, we can prove E2, then we can go back to the original gamma that can prove that the lead expression is of type T2. Because we're now binding the free variable x as E1 in my program, so I don't need to assume the type of x anymore in my gamma.
Right.
Why? Because x is bound to the value E1. And we've already assumed that E1 is of type T1 in the original gamma. So maybe we should just put a parenthesis around the expression here. Can you put a parenthesis around let x equal to E1 in E2? This is, yeah.
Like
That
that.
whole thing, yeah, that whole thing is of type T2.
Right. It's not the
Yeah.
E2, it's the whole thing. Right.
I was trying to figure out how to sound this out in my mind, and I guess it might be something like when you say gamma turnstile E:(T, it's something like gamma proves that E is of type T.
Yes.
Yeah, kind of.
Right, or in the context.
Given the
of-
assumptions in gamma, you can prove.
Yeah.
Yes,
It would be interesting if we, in this formula, if we left out all gammas here and just state E1 is of type T1 and X follows T1. And so I think if we leave out all the gammas in this formula, it makes also sense. Different one, but you could
Well,
derive the same thing.
not quite. You have to, the gamma is to keep track of the types of variables. If you have a language with no variables, then you need no gammas. But in this particular rule, the let rule, you are binding a variable. So you are talking about two different contexts. There's the original gamma, and then on the right-hand premise, there's gamma supplemented with x:(T), or x:(T1) rather. And so that you have to be able to distinguish between those two contexts.
Right. What if E1 contains another free variable like y, right? Like it's 1
That would
plus
have
y.
to be in gamma. Right.
Yeah, then how do we know what the type of y is? And so, yeah.
But
Because
Andrea is not wrong, because most of these rules make perfect sense if we take away the gamma turnstile. I mean, for example,
Right.
the one at the end of that
Well-
line just says if you have an E which is bool, then you also have not E which is a bool, and that's an expression as well. So a lot of them, a lot of times you don't need it, but as Adrian was saying, sometimes you do.
Right,
need to-
you need it if
Well-
the expression contains variables. You have to get the type of the variables from somewhere. But if you don't bind any new variables in a particular expression, then the rule for it will, all the premises and conclusions will use the same gamma.
Right.
So I have a question for
So the one thing to understand is that these rules are schemas. They're true. Basically, all these symbols are basically meta variables that you can instantiate with anything. So, right, if you have a rule with gamma, one possibility for gamma is that it's empty. So you could just specialize the rule to gamma with empty, and so then you wouldn't have anything here or here, but you'd still have to have x:(T1) here in order for the rule to work. I don't know if that made sense.
my question is if in the assumption line above, the first expression, it ends with T1 and then we have gamma, comma. But isn't that redundant because we know already gamma, we have already gamma there. So gamma exists, we can't take it away. So we can write just X, a double colon T1. And also T1 was already introduced, so all we need is it exists. and from there follows E2, T2.
See, these things are independent, though. These two premises.
Yes, they are
Just because you
independent.
have gamma here doesn't mean that you have gamma here. You have to explicitly write it.
Sure. I think it's someone, I understand it as a statement which establishes some truth in one step. So if we have gamma, we have it. We can't take it away. But it's my understanding.
Okay.
I kind of have a slightly different opinion. I think you're saying that the line above the assumption, both the second one is redundant, right? But I don't think it's redundant. It's saying that X, because in X was not in the original gamma, so you have to define what X is. So you have to augment the original gamma with the X of type T1 so that E2 can be defined properly. Is that what you're referring to?
Yes, I thought we have already T1.
But you don't have X.
No, we don't have X, but when we address X to T1, X gets known too. Because it doesn't follow from gamma here. It's just a comma. I understand
It's
it as
adding.
it's just in the declaration gamma exists, yes, but I know it exists.
Right, I'm not sure what you mean by.
It's not that gamma
exists.
exists. Go ahead. Sorry.
So I read it as redundant somehow.
I feel you
I'm
read it
wrong.
as redundant is that you assume that the let expression of X equal to EY allow you to infer the type of X in E2. That's why you think it's redundant, but I don't know if that is sufficient.
In order for this to be well formed, by the way, X cannot be defined in gamma. Typically, that's sort of a meta rule. So this gamma doesn't have X defined in it. And that's fine for proving that E1 is T1. But to prove that, this part works, you need to know that X was defined and that it had type T1. So this premise is proving a different thing. It's proving something about E2. And because let introduces a variable, we have to characterize it in the environment.
I will, thank you. I will reflect it further.
Okay.
This is kind of it's a bit of a tangent and criticism too, but like this notation is supposed to aid in, I guess, I'm assuming like accuracy and precision, but as we can tell here, I mean, it's like there's multiple interpretations. So what's going on?
I don't know that there are.
Well,
or it's just, yeah, I don't
once
know.
you get into sort of regular, language design, these rules are pretty well defined, and there aren't really multiple interpretations.
So yeah, so I guess it just depends on the background.
Well, you see, if you
knowledge.
are suppose you're implementing 25 different programming languages. They're all slightly different. They all have slightly different keywords, but they're all the same kind. They have the same idea. They're functional languages. They have types. They have expressions, and so on. So this is a standard notation for that. So then, if you have done that, then it will be easy for you to write this.
Okay.
But however, that said, there are a lot of non-standard symbols here, like all these tensors and other things which are confusing. So some of them are just operations in the language. It would be perhaps better to have names for them, like keywords. So essentially, this table is a very condensed notation for a type checker. Right, so if you read this notation and you translate that into an algorithm for type checking, then this would be a good understanding of what it is. So gamma represents, so your type checker needs to be recursive. It goes by recursive descent on the expression. Then you look at the rules. At least one rule must always match. And you go into that rule and you call recursively the same type checker on sub-expressions and so on and so on. So essentially, if you want to write a type checker for this language, this would be your specification of what needs to be done, how the types are found for your language. Now this is yeah.
Are some of these symbols overloaded too? Is that why, depending on context,
No, actually, no. So,
No.
you need to understand what symbols mean what. But just imagine you're writing a type checker. So you have some expression that you need to type check. It has some sub-expressions. For example, let's suppose this is if, then else. You're trying to type check if, then else. So then you have 3 sub-expressions. You call your type checker recursively on the 3 sub-expressions. You get the results. Well, either the type check or not. Either the types are matching or they're not matching, right? So suppose they're not matching. Then you print an error. This sub-expression should have been of type bool, but it is not. Well, end of story. So you have an error message. And if it is of type bool and you go on, or E2 and E3 must be of the same type. Type checker tells you that they are of the same type. Excellent. Now you have found that this entire expression now has type T, and this is the return value of your type checker for this case. So the gamma represents the variables that you have type checked until now, or expressions that you have type checked until now.
Within the current environment. So so this notation, this table we're looking at, it's standard notation then?
Yeah.
So then going back to example 2, what's going on there then? As far as Peter not
This one.
Yeah, that we're talking about, like what's going on? Yeah, what's happening there? There's a disconnect, right?
Well, I'm not sure.
Well, Peter didn't get his initial answer, his initial question answered, so.
Right. My question was, if these things are semi-dictionaries, right? It's not saying semi-module, it's saying semi-dictionary, I guess. But wait.
Semiring dictionary, right? SD is a semiring dictionary.
Right. So the original question is, if you multiply 2 dictionaries of the same type, why do you not get a dictionary of the original type? And I think we've answered that. You get a dictionary of a type that is the tensor product of the inputs.
Right. Now, let's go back to the type checker table and see where that is. Where do you multiply dictionaries? Because some part of it must tell you how to multiply.
Right, it's the rule.
It's this one, right? Exactly,
Yes,
exactly. That's this one. So then it tells you that the result of multiplication needs to be of a tensor product type, and it is not the same type. It's not neither T1 nor T2. It's a tensor product type, and T1 and T2 must be semi modules. So you so that seems to be consistent. The only problem here is that this tensor product
Hmm.
type is not an easy operation to describe. So this needs to be described separately. It needs to be understood what that is and how do you construct a tensor product type. Okay, but they explain that in the paper, right? Definition of tensor product. It's in the left bottom corner of this table. Definition of tensor product. So
Well, that's what this part is, right?
yeah.
Yeah.
And it's not easy to understand that because that's actually not a it's not a type checking rule. It's kind of a syntax sugar of some kind, right? So they tell you what it means to have a tensor product with numbers, a tensor product with dictionaries, tensor product with records, and so on. So it's okay. Anyway,
I guess that equal sign with the little delta over it means like equal by
equal by
definition.
definition. Yeah, equal by
Defined to
definition.
be equal.
Yeah, yeah. I'll step out for a while.
But there's a rule here for like a dictionary being product with, or tensor product with just a regular type, but I don't see that there's that any place where you can take a dictionary and do a tensor product with a dictionary.
Well,
Uh,
Which is kind of what that
T0
T0
itself,
can be a
was.
dictionary.
T0 itself can be a dictionary type. Yeah, sorry.
Yeah.
Maybe.
Yeah.
No, we were talking about the same thing.
Oh, yeah, you're right. Okay. Because types include, yeah.
I am a little puzzled that there isn't a tensor on the other side as well. Like,
Right.
what happens if you
But
try
yeah,
to
I guess part of what
T0?
I'm saying is I don't see any rules that would tell me how to deal with a T1 arrow T2 on the right side. But maybe
Right,
I
but
don't need it. because it
T0
just-
is universally quantified, so it works with any type, including dictionary types.
I guess actually the rule to the left could work, right? Because the rule to the left shows scalar tensored with any semi-module type, right? Scalar tensor S tensor T1. And in particular, T1 could be a dictionary type, which is in semi-modules over S. So it could be a dictionary type with values in S, for example. And that would be.
Are you
that
talking
is-
about this rule?
No, sorry,
Oops.
just to the left. The one just before it.
This one.
Yes.
Yeah.
Okay.
So T1 could be a dictionary type there. And that shows what happens when you have a dictionary type being multiplied by a scalar type on the left.
Oh,
But oh,
okay.
actually, no, I'm sorry. No,
yes.
your question, you wanted to multiply two dictionary types, so my comment is not that helpful. So yeah, I think we go back to what Wei Ning was saying about the original rule about T1 arrow T2 tensored with T0, because T0 itself could be another dictionary type.
Yeah, that's the case I was thinking about. But I guess what happens is you kind of get inside this record and you have the same keys, but then you take whatever the value is and multiply that by that. But now this is likely to be a scalar. And so you're just
Or at
doing
least
the
a smaller
scalar
expression.
multiplication on that other dictionary.
Yeah.
Right. So, yeah. So if, where are we? If T0 is like T3 arrow T4, then we'd end up with T1 arrow T2 tensor product with, what did I say? T3 arrow T4, which then you can push assuming this is a scalar, you can push that inside. But you still end up getting a dictionary of dictionaries, which is what their example shows. And I guess that follows this rule. It's just that I thought the multiplication had to be closed over the same set that you were dealing with. But,
Yeah, it seems like they're saying that, but if they do, they're wrong, or they're saying it unclearly.
Right, I think that's true of semi-rings, but not of semi-modules.
I'm also curious about an earlier comment that Adrian made about their types, that you have to know the depths upfront. Is this where the limitation is coming from? The way they define, they build up on their complex semi-module types. That basically you cannot just, it's not closed under tensor product, the type.
Right, right. Multiplication is not, yeah. Yes, the type is not closed under multiplication, except in the case where you have a scalar semi-ring, you'll wind up with the same type. The tensor product of S and S is S. But if it's more generally, if it's a semi-module, then we'll wind up with a different type.
okay.
I guess the kind is closed.
Yeah.
In the sense that if you have two types which are both semi-modules over S, then their tensor product will also be a semi-module over S.
Yes, that would have to be the case, right? Yeah.
What is it? Now, let's see. Dictionaries. So that here it's talking about semi-rings, not semi-modules, right? Then the dictionary also forms a semi-ring. Right, so V here is not a semi-module, it's a semi-ring. And this is supposed to form a semi-ring.
I think when they say
But
it forms a semi-ring
semi-rings
structure.
are closed. What's that?
Sorry. Yeah, I was reading that as the dictionary should also form a semi-ring, but it doesn't. And I think when they say it forms a semi-ring structure, they mean like a structure related to semi-rings. I think it's more vague than we were.
Oh. Huh. Yeah, I mean, they say it's so weird. The value of elements of type V form a semi-ring structure, rather than saying V is a semi-ring.
Right. Well, the semi-ring would be the type plus the operations, right? Type, operations, and laws are make
Right.
it.
That's the way I think of it. Yeah. So V here would be a type, and it would have, you know, those operations plus and times, 0 and 1. And then it seems like they're saying that then if the dictionary has values of that form, then the dictionary also forms a semi-ring structure, which would be then the type is the dictionary type, and there would be plus and times on that type, as well as 0 and 1 on that type.
I think they're just writing it confusingly.
Yeah, I think they're writing it confusingly. They either said the wrong thing, or by semi-ring structure they mean something more vague than an actual semi-ring.
Okay. Okay. Oh, this has gotten in the way. Or we get rid of it. Wait, what's going on here? Are you still seeing my, oh, it's paused. Did it go away? Oh, resume share.
I don't see you doing anything. I still see the top of page 4.
Okay, is it moving? I'm just not seeing it.
No, I don't see anything moving.
No.
All right.
Shoot. What's going on here? Hang on a sec.
You might want to restart your screen share or something.
Yeah. Okay. Yeah. Stop share. Share. Oh, to come back. Now it's
Yes.
now it's moving, right? Okay. I don't know what happened there, but anyway. I had opened up the PDF of our stuff, and it came on top of this, and I couldn't move it because it was kind of hidden. Okay. Okay. Yeah. Okay. Let's see. Was there something else I wanted to say here? Yeah. I was just a little confused, and maybe this is part of what we were talking about. Is here they're saying types with semi-ring structure have kind SM of S, but then they say that a semi-ring module has kind SM of S. So is that the same kind?
Value types also S.
But yeah.
Right. It's just saying that a semi-module, if a semi-module S is the value type for a dictionary, then the dictionary is also a semi-module of S.
Yeah, I think that's how I would interpret it also.
Well, yeah, but that I think that's later. This is just talking about this kind here. They're basically types with a semi-ring structure have this kind. And then they say
which are ints and
semi-ring dictionaries have this kind. Oh, it doesn't talk about dictionary. Yeah. Okay.
Semi-ring dictionaries with that value type is also a semi-module. They're talking about the how the value part of a dictionary affects the type, affects the kind.
Yeah. Okay. And I guess the point is the semi-ring is a semi-module, right? It's a
right.
If S, yeah, S is of kind SM of S because, right.
Yes.
Yeah, the semi-ring is the first trivial example of a semi-module. And then you can use it to build up more interesting ones.
Okay. All right. So expressiveness for, we didn't do set and array. Oh, we didn't do dictionary summation. Do we want to go through any of that? I mean, I think the set and array are kind of interesting. Basically, arrays are obtained by using the dense integers as keys. So they're contiguous integers going from 0 to k. And that's
Right.
how you get
Yeah.
an array.
Yes. All their data structures are sort of stuffed into this dictionary
Framework. Yeah.
framework. Yes. So you have, the record type is basically a dictionary of field names to values, and the dictionary of course is a dictionary, and the set is a Boolean valued dictionary, and an array is a dense int keyed dictionary.
Right.
It's a little bit like PHP, but not very much. Anyway,
I don't know what oh,
it's not important.
the web language.
Yeah. So
Yeah.
they have arrays, but the arrays are like dictionaries underneath.
Mhm.
Okay. And then sets are basically dictionaries where the range is Boolean. And so yeah, so basically you have a bunch of keys, and those keys that go to true are the ones that are in the set. And anything going to false isn't in the set. And
Right.
they have a rule that you don't have to write in the set brackets things that go to false, or things that go to the whatever in general, if the range is the 0 of your value type, then you don't have to express it.
Right.
And so the 0 bool is false, so you don't have to write anything that goes to false. You just write the ones that are true, which makes it look like a set.
Right. You can't distinguish between absent values and 0 values.
Right. Yeah.
But this is just an arbitrary choice, right? I'm saying that your value type can be anything. Actually, you just differentiate it by key, and you will have a set as well.
Wait, Adrian, you said it cannot differentiate between absent and 0?
Right. Yeah, that is their convention. So if you have a dictionary, some of whose values are 0, then you just drop those.
There was an example that had those somewhere, but not seeing it right away.
So if you have a dictionary from string to int, and it's like a maps to 1, and then you have another dictionary where a maps to -1, you can take the sum of those two dictionaries and you get the empty dictionary.
Yes.
Are you
Maybe we
losing
can
anything?
define
Do you
minus on
lose anything when
dictionaries.
do you lose anything when you do that though? I mean, no?
Well, you lose the ability to say whether you had an entry for a at all. Yeah, so you have to be okay with the idea that a 0 value is the same as an absent value.
Right. If you have a dictionary taking keys to -1, that's not really a set. That's an anti-set. And you combine it with a set, and then stuff that's the same goes up in smoke. They cancel each other.
Yeah,
But
I was
they
just
don't-
wondering, like, from like maybe I don't know if the right word is heuristic or this kind of general rule of thumb thing, is it if that's kind of kosher to do or not, but it sounds like it is then, huh?
Well, I think it depends very much on context. The particular application for your data, you have to know whether in your business logic, as it were, it's okay to treat absent values as zero. If it's not, then you have to choose some other representation.
Okay, so context specific then. All right.
Right.
Yeah, that makes more sense. Or at least sits better with me.
Right. So expressiveness for databases. Hugh, did you go through this? Do you want to talk some?
Oh, I think we're going to hit one of my questions pretty soon. But I want to make sure that other people have the opportunity to raise questions as well. Does anyone have a question from sort of here-ish, or maybe earlier on that they wanted to get to?
I think we should just
Good
go
point.
over the definition of the sum, because I found that a little confusing. But I
Oh, where's
needed to
that?
right above there. There it is, 2.4.
Dictionary
Oh,
summary.
okay.
Oh, wait, we're 2.4.
Section
Yeah.
2.4. Yeah. At first, I
Okay.
wasn't sure what they mean by sum. I thought it was a map kind of operation, but it's not. It actually is summing. So that the example they give, example 1 continued, so if you have a dictionary and then you have an expression sum x in d x dot val, then x is bound to the both key and value in that dictionary, and then x dot val picks out the value, and then you sum up all the values. But then the next
So
sentence,
yeah, so
yeah,
just so basically, yeah, you go through your D, X is representing each one of these things where
right,
dot
key value
key,
pairs,
X dot key is A, and X dot val is 2,
right,
and then you take, and then you evaluate this expression with that X, and then you sum them all.
right. But then the next sentence is now instead of val, we now have a dictionary as the expression. So you have sum angle bracket KV in D, and then you have this dictionary as the body. And then there it does act like a map, but they also call it a sum because the two dictionaries, A into 2 times 2 and B into 3 times 2, they can be added to create a dictionary that has both key A and B. So that's
Right.
Right.
a little overloading that I didn't like, but it's okay.
There's a subtlety, which is that a dictionary where you don't have a particular key, it maps to the identity of whatever that is.
To the
So it would map
addition,
to 0.
right?
So when you add the two things together, then if there's a key in one, that's not 0. And if you add
Yep,
it to 0, it's the same thing, so you end up with both keys in, both pairs in the dictionary.
right.
But
When
yes, it's
I
very subtle. It follows from their rules, but it's subtle.
Hmm.
I share Young's kind of like confusion a little bit when I read it. When I kind of feel it, sound like it feels more like fold to me. Do you feel that way?
More like what?
Fold, a fold
Fold,
up a
yes.
Mhm.
Fold.
yes,
Yeah, yeah. It is a fold, except that
uh,
the operation is the addition for
yes.
the semi-ring. Yeah.
Mhm.
And then
Oh, I see what you're saying. Okay.
extending that to the addition of dictionaries was the part that, yeah. So they're using the sum to do both. regular numerical sum, but also kind of a map operation where you have dictionaries that produce a new dictionary. So,
Right.
okay. Yeah.
It's kind of a map reduce. Yeah.
But they
Yes.
don't, yeah, but they never have, I guess, getting back to what Sergey was talking earlier on, they never talk about fold as such. And in fact, there are no function types here, unless I missed something, right?
A dictionary is a function type.
Yeah, it's like a little bitty function maybe, but yeah, increment, for example, there's no way in this language to say that increment is a function that takes an integer to an integer.
That is true.
Right.
Because we're not being specific about the scalar types. So you can have int,
Right.
real,
There's
bool,
no arrow type.
but then you have these max m's and so on, which don't have an increment defined, right? Like max sum type and max min type, we don't have notion of an increment there. So
it's more like SQL than it is like a general purpose programming language.
Right. Yes.
which is what they're getting at, I think.
Yes.
But you can't even write increment on like integers, right? There's no lambda. There's no way to form
No such thing as a function. Yeah.
Right.
At least not in the language, this
Right.
part of the language.
I mean, you can create a new dictionary where the values have been incremented from some previous dictionary, but yeah, the increment is there's no standalone function that doesn't increment.
I suppose you could introduce a constant 1, and then you can do x plus 1. But then that constant 1 is only appearing in the int and num structures and not in the max, the min sum and max sum. I don't know if you can increment by 1 and make any sense. Oh, they do have 0 and
Well,
1
they have,
defined.
They have a 0 and a 1. Yeah.
yeah,
Yeah.
right.
But you
You
can't
But
do
you can
increment
by
1.
1.
You can,
So-
it just because you have addition and you have a 1, so you can just do it.
Right.
But,
Sometimes the 1 is 0, but
Yes.
Yeah. Right. So on some of them you can, and some you can't. So
Well, you have a 1 for basically any of these semi-ring structures. So you can
the
increment
logic,
any semi-ring element.
I thought that even though call it 1, it's just an identity for multiplication. It doesn't mean
That's
anything
right.
in terms
Yep,
of the
that's
1
right.
for increment. Yeah.
right.
yeah,
Well, that's a point.
yeah.
Yeah.
Anyways, I thought
So
that
your
was
increment, but your increment would be defined. Yeah, never mind. But we can't, but the point is we can't even define increment, even if we could agree what it should do. Because they don't have a way of defining functions.
You have to define an extra successor function kind of things to do increment. Right?
I guess what Adrian was saying is we can do it, but we can't say in the language that we can't exactly say it in the language that we're doing it.
Right. We can do things that increment, but we can't have increment by itself as a
As a thing.
standalone expression.
Right. We can have increment coming in from the outside as part of like the int type or something. We know maybe that there's an int increment, and we can use that, but we can't define it in this language.
right.
Okay. And like this domain thing that gives out the keys is because you're summing up these sets, singleton sets that have these keys in them. When you sum them up, you're basically taking the union of all those sets. So you end up with the set of keys. I had to think about that for a while.
Right.
I guess you're replacing all the values with true, basically.
Right. This says this is the set where x dot key goes to true and everything else goes to false.
Yeah.
And then, you know, so you go through all the keys that way. And when you union them, all the keys map to true and everything else maps to false.
Yeah, that's the kind of abbreviation that I find confusing unnecessarily. Because you're using the sum
Yeah.
notation, the thing there needs to be something, either a dictionary or a scalar. But now they've got a dictionary with only one element, which to me is ill-formed. But yes.
Well, it's actually a set with one element. The dictionary would be
But a dictionary, sorry, that is implemented as a dictionary.
Okay, I see. So it's a
right.
set with one element, which is a dictionary with that key mapping to true. Okay.
Yeah.
And everything else mapping to
Right.
false. Okay.
Right. Were there other questions that before we go on? Okay. Expressiveness for databases and the relational algebra, which is, you know, what's behind SQL and all the relational databases. Are there any questions here, or Hugh or somebody want to go through it? Or
Figure 4, I found a little puzzling. And I think I know what they're doing. They're taking the basic concepts of relational databases and showing that you can express those in the language that they're outlining. But
so right, so yeah, so the way they express the relational database is as one of these maps where the domain, the keys are these tuples, or are no, actually they're these records, and then there's a bool saying whether it's in there or not, right? So like this selection thing, basically you're saying if, you know, here the key is the data, it's the record that has the data in it. So you're asking, is P true of that thing? If so, then create the singleton set with that data, which is the dictionary with that data going to true.
maybe I was wrong to say
all those.
Sorry. Maybe I was wrong to say there's no function application in the language, because I mean their notation is pretty loose,
Doing
but
it here.
does look like P is a function and F is a function.
Right. I think they'd have to come from outside, right? Whatever you're, yeah, well,
Right. This seems like a somewhat loose
because P would be over a record, so it's hard to bring it in from outside, but yeah. Adrian, sorry.
Yeah, it looks like a somewhat loose translation.
Right.
The other thing that bugged me was these double square brackets.
Yeah,
These
that's a pretty standard convention in semantics, where the double square bracket just means the meaning of the expression sigma PR. So now we're talking about the inside the square bracket is the language in SQL. And then, so we're now translating that into something that's in our language. and then inside you have X in R. So now we have recursively, now we've made the object language smaller. So
Right.
in
It's,
denotational semantics, the square brackets are used to quote the object language that you're translating.
right. So this is a recursive function, is what it's saying.
Right. Right. The translation of this involves the translation of that.
I see.
So
So if you
yes,
have an
it's
expression
recursive.
in square brackets, you should be able to use these rules repeatedly in order to reduce it to SDQL.
Correct.
Yeah.
Yes.
Gotcha.
Right.
Now, there's no base case in this particular algorithm because there's no translation that doesn't have brackets in it. So it's you can't just run this as is, but
It's a sketch.
They must have it somewhere, though.
well, yeah, I assume they have figured this out completely, but they are being a little loose here.
Yes. I think for the, there must be a primitive types. Oh,
It's
there's a
like
next figure 5. There's a next page.
Well, before we go to that, I mean, I think what they're saying is, okay, in your database, you have a table, it looks like that. And in this language, it's represented by a set like this. So this is kind of your double bracket translation for tables.
Mm-hmm.
Does that make
That's
sense?
true. Yeah.
Yeah.
Cool.
So what were you saying about table 5? Is that what?
Yeah, the translation
Yeah.
continues. Yeah.
Right. Oh, this is a translation from a different language, and our C+ and relational algebra are slightly different things.
I see. Yeah, they are different.
This one's NRC and this one's relational algebra, whatever. Yeah. So yeah, I don't really know what these things are, but you can kind of see that these rules probably make sense. You represent bags by key to number, and so the empty bag, everything maps to 0. The singleton bag, you just have this one thing mapping to 1 and everything else maps to 0. And I don't understand the rest. So anyone want to talk about how that works? Like these things seem like monadic, right? Flatten and bind.
Yep. So flatten just takes the pair key value and just multiplies them together. Unless that's the tensor product that they're doing, because they mentioned that they use the same star asterisk for both the ring multiplication and tensor multiplication, which is again confusing. I wish they didn't, but I guess they don't know how to use a different character on the keyboard. So
Yeah.
I find this kind of overloading and at this level, confusing, unnecessarily
Very
confusing.
annoying.
Right. Well,
Yes.
for
Yeah,
a given pair of data types, you can only do one of the operations. You can either do the tensor multiplication or the scalar multiplication, depending on the input types, but you can't choose. So it seems
right, but you have to
Okay.
kind of go through the whole type checking algorithm to figure out which star it is, and that's too much work.
But this does depend on some stuff about the types, right? So the keys are not strings here, for example.
Right.
Right, not necessarily. Yeah, you
Well,
can't.
I don't think they can be, because if they're strings, we have no
can't.
way to multiply them.
Right,
Yeah.
right.
Right. So V, I guess, the range here is int, right? Because it's either one or multiple, I guess. But then it seems like you're taking, you know, if you have two things in your bag, then when you do this flattening, you have only one thing in your bag, but it's been multiplied by two,
Hmm.
whatever that thing is.
Right. Okay.
Is the result a
Bind.
bag? I guess it has to be a bag, because sum always produces a dictionary. So it's not a scalar in particular.
Unless the V times K is a scalar, then you're doing a literal summation, a reduction, or a fold.
Hmm.
See,
Yeah,
this
if
again,
K was also int, then this would be
Yeah.
an int, right? And you'd just be summing them up.
right?
No monadic bind for X in E1 union E2. Basically, you go through your E1 and multiply the values times whatever your E2 is.
Hmm.
Seems
I
like
see
you're
that we're-
losing your X.
I see that we're running out of time.
Oh, yeah.
We are.
So yeah,
I guess the question is, have we talked about all of the interesting parts of this paper, or do we want to do more of it?
I think do more sounds kind of
Yeah.
what I
So
vote for.
those who have studied until the end of the paper, what do you think? I have not, so I can't comment.
As they go on, they're talking more about I feels to me like implementation details or applications that are maybe less general. So I'm kind of feeling like we've talked about the high level part of the paper. But if you know, we can if people are interested in the specific applications of this thing, we could go to the end.
right. We sort of talked about the general framework, but then they're talking about how you can, you know, do databases in it and linear algebra in it, vectors, matrices, and that's about it. And then efficiency, there's a bunch of stuff about, you know, making the queries more efficient, which I guess is part of the key feature of this.
Right. So I guess we could take a vote. More of this, or pop back to, I guess it's chapter 13 of the Science of Functional Programming. Anybody vote to take a vote?
Sure. Yeah, voting sounds good. I'll vote to continue on with this paper.
Okay.
I'm for dictatorship here by Sergey.
I
Right.
think
My
on the
vote.
whole, I'd like
What
to
was that
continue
vote?
with.
You'd like to continue? Okay. My vote would be to go back to SOFP. anybody else?
Yeah, everyone's got to vote. Throw
Yeah.
your opinion out there.
Well, I think you could abstain if you know.
Yeah, okay.
Right.
I don't feel
right.
strongly about it. I do wonder whether, I know that Sergey picked this up initially because of some connection, presumably, with the science of functional programming and what he was doing in there. And I wonder if we've addressed that at all.
Yeah, I don't remember what.
Yeah, at the beginning he was saying that he was expecting there to be like a do notation. So maybe he was thinking that this had more of a connection to monads.
Maybe we could split the session
But-
next time.
No, I mean, I'm fine. I'm fine either way. So you guys, I mean, let's just take the vote and go whatever.
Yeah, a split session is actually, we could maybe like spend
Good,
another
huh?
hour on this and then
Okay.
go back
Okay.
to chapter 13. That's probably
Reasonable
the
compromise.
best way to do it. Yeah.
Okay. So
Okay, I'll vote for that.
yeah, I'll vote for that. Do
Okay.
you guys have any recommended like more basic or elementary resource that would complement this paper? Anything come to mind?
No,
I mean,
really.
the problem for me is that I'm not very familiar with all of the applications here. So basic material might be, you know, sort of a book on relational databases plus maybe the Semiring article in Wikipedia. I don't know.
It's it's kind of a broad paper then, right? Relatively speaking, or it just pulls from a lot of.
I mean, yeah,
Yeah,
they're
it does
doing a
pull
bunch.
from a lot of different places.
Yeah, that's my impression. Yeah.
Yeah, they're doing a lot of original work and yeah, synthesis of a bunch of stuff. And
Yeah. Yeah.
so yeah, it's all over.
Okay.
I mean, they talk about a whole bunch of gene sequencing examples and things like that, and they seem like they get pretty specific about what they're talking about. But it's just an example. I'm not going to go and figure out what
The stuff
the
that we're,
genes, what
yeah.
they're
I mean,
talking about there. But this things
Yeah.
like linear algebra, matrices, and those things are all pretty standard.
What about the stuff that we're talking about today? Does this fall under the umbrella of like type theory or something like that, or what?
Yeah, almost, and the notation that we were talking about, the natural deduction notation for type checking, you'll find that in almost any paper on type checking the language.
Where'd it go?
It's page 4. Yeah.
Yeah, I think
that's
I got
fine.
it.
But where would you go to learn that notation?
Where would you go to learn that? I don't know. Maybe
I would go to Pierce.
Yeah, Pierce.
Pierce, huh? Okay.
I wonder.
Types and programming languages. Yeah.
We might want to try getting the new folks onto Slack, and then we can
Yeah.
throw
Okay.
more research suggestions there.
Okay.
I mean, yeah.
That sounds good.
Anyway, thank
What are
you.
you
I'm
saying?
gonna go.
Yeah, thank you. Thank you, everyone.
Yeah, so
All
2
right.
weeks from today, is that a good meeting time? 10th of February?
Works for
Works
me.
for me.
All right, then, let's do it then. Okay, see you all then.
Okay. Bye.
Thanks.
Yeah, see you
Bye.
guys.
Thank you.
Bye.
Thank you.